Okay. Good afternoon. Welcome to, which one is it? Mechanisms and Machines. I have a few announcements to make regarding the organization and the plan for the last 2 weeks or the next 2 weeks. So the first is that marks for the labs are popping up on LMS as we speak, right? So so the first lab, this engine assembly, so there was no report, so there is nothing to report on LMS. But the newer lab marks are already there, so please check whether you got what you think you got. Yes? Yes, it was, but based on attendance, right? It's in the handout how much it was worth. I don't remember. And your demonstrator, Johan Rowe, is the guy responsible for newer marks. So if you have trouble with the mark, go to him. And actually, there was a class email sent advertising when exactly when and where the reports can be picked up. Now, picking up lab reports for some of you may be important and worth doing, because if, God forbid, any of you fail the unit and then are forced to redo the unit next year, I normally allow or do not require repeating the labs, provided that I am shown the marked report from the previous year. Okay? I'm just taking the view that if somebody cannot show the marked report from previous year, it means he or she didn't care and therefore has to redo the lab. And actually, this is the university regulation that the entire unit should be repeated, and I sometimes deviate slightly from the university of regulation and let people skip the labs if they are repeating the unit. Okay, but they must show me the marked lab report. So this is one thing. The second thing, the marks for your assignment are being generated as we speak and should be on LMS by lunchtime Tuesday. Okay, maybe earlier, but barring some unforeseen circumstances, they should be on LMS by Tuesday. And during Wednesday lecture, which will be 1 p.m. Wednesday in Ross, there will be formative feedback given on the assignment, and assignments will be retained. Okay? So the tutors will be here. You will be able to get your assignments back. The marks you will already know probably by the time. And then the tutors will give a presentation about what they consider to be perfect or close to perfect, very good submissions, and what were fatal flaws in the submissions which disqualified essentially the submissions. Okay? And then on Friday during the lecture, the tutors will be here again and will be able to answer any specific questions that have not yet been answered in the general feedback given on Wednesday. Okay, so if you find something you are unsure about, and if it is not covered during Wednesday lecture, okay, because this will be not a specific feedback for everyone separately, it will be a feedback for the entire class. But the specific feedback for groups, which is not covered by the Wednesday general feedback, will be given on Friday during the lecture. So simply tutors come here, and if you have queries, you go to them. If not, tutors will go to their other duties after 10 minutes or 15, right? Which means the normal lectures which I will be giving will be today, Monday, next week, and then 3 lectures in the last week, because Wednesday and Friday will be the tutors will be here and dealing with your assignments. Okay? And the last item, you see, Andrew Guzomi and I received a small grant which is the grant to improve student experience or something like this. Okay, this kind, I don't remember exactly, and with the idea to produce short, informative videos, okay, explaining major threshold concepts and giving solutions or explaining the solutions to example important problems in the units ENSC 2001 motion and ENSC 3001 mechanisms and machines. So the plan, of course, was to have the videos up at the end of the non-teaching break at the latest, but the plan was a bit affected by the failures of recording equipment and misunderstandings with IT on what's required, what's not required. But again, I would, as if I were you, I would keep checking LMS whether these videos are not popping up one by one on LMS. And if they pop up, they would probably be popping up towards the bottom of the page where I have the topic called Hints for the Exam or Preparation for the Exam. Okay, so there are already, I think, 2 documents there, but then videos with some hopefully sensible explanations should be there as well. I would like, if possible, to receive some feedback whether these videos are of any help or not, right? So when you one day decide to fill in a SAFE survey, maybe you will have a chance to make some comments. Maybe you could comment on this, or in the email directly to me. Right? There is some, you see, idea that because of the generational gap, the old people like me don't understand how young people learn, and that videos, YouTube actually is more effective than reading from books or things like this. Whether it's true or not, I am not sure, but I will welcome some feedback on these videos, and I am the plan is that they should be popping up before Monday lunchtime. Okay, so over the weekend before Monday lunchtime, there should be something there. Any questions about these organizational issues? Okay. So back to our 3D magic or gyro magic. So today we will consider a steady precession of a gyroscope. And here we have the picture. Okay? So we have a symmetric or axisymmetric body, or the rotor, or a bicycle wheel, or a rotor inside the gyroscope I showed you before, spinning rapidly around axis Z. Okay? And then we have also this gyro precessing slowly around axis Z1. Okay? So it's spinning rapidly with angular velocity phi dot and precessing slowly with angular velocity capital omega. Okay? So the angle between the axis of spin and the axis of precession on this one is capital theta. if you remember the gyroscope I had here, right? So this angle was 90 degrees, right? So this was the plane of spin, and this was the axis of precession, right? So the angle theta was 90 degrees for the thing we have at the lab and I showed at the lecture, right? But of course, it does not have to be 90 degrees. It can be something, okay? So now we want to understand what forces or what moments are needed for this steady precession of a gyroscope, okay? And for this, we have our cool green equations, right? Green and red and blue. So these are the equations from Wednesday. So the Euler's equations of rotational motion in vectorial form, and then even in red in a scalar form. So say coordinate axis form. Now, if one is not that confident with doing these vector products and the like, we have a Mathematica file which does this, okay, and it's on LMS. So notes on derivation of Euler's equations, okay. So if this is the angular momentum, and this is the angular velocity of the coordinate system, you are interested in doing this cross product, right? Cross omega times h, right? Which in Mathematica, the command is cross, okay? And I call this second term because this is the second term, omega times h, right? So you get this, which will be the same as this one, and this one, right? And if you wanted to consider the special case of a symmetric body, right? So principal axis of rotation, of symmetry, or of inertia, and therefore all products of inertia equal to 0, you get this, which will be the same as the blue stuff here, which we derived on Wednesday. Okay? So if we are convinced that these equations make sense, we simply need to apply them to the gyroscope, steady precession of a gyroscope. Okay, so this, I'm displaying this just so that it gets recorded. We want to specialize Euler's equations for a case of a steady precession of a gyroscope. So, of course, the first question is where to put what coordinate system to use. Okay? So what are we using? What will be the good coordinate system for our gyroscope? Where will we put the origin? Center of the gyroscope, meaning the center of mass, or meaning something different? We want to put the center of the coordinate system at the fixed point of motion. Okay? As it happens in this picture, it is also in the center of the gyroscope and in the center of mass, right? But it does not have to be. The important thing is that it must be at the fixed point of motion. Okay? And then, of course, we must have our matrix of inertia constant, right, in our chosen coordinate system. So how would we choose the coordinate system so that it has the center at the fixed point of motion, it is convenient, and the matrix of inertia of a gyro remains constant in that system? So, tell me. Well, by say, elimination, well, it can't be the inertial system fixed to the ground, right? Because the gyro will move in it, and therefore the inertia would become variable in such systems, so it's a disaster. So we want the system that there are essentially two possibilities. One, we just fix the system on the body, right? So the system fixed on the gyro and moving with the gyro, right? Well, this is doable, but the better choice is to put the coordinate system in such a way that it precesses with the gyro, but doesn't spin. Okay? So even though then it is not completely fixed on the gyro, the inertia matrix remains constant because of the symmetry of the gyro, right? So this is how we set up the system. X, Y, Z, okay? And this system precesses around vertical axis with angular velocity capital omega, as the gyro does, but the system is not spinning with the gyro because we don't need it because of the symmetry of the body. Okay? So now here you have an example of a coordinate system in which the inertia matrix is constant, but it is not completely fixed on the body. And that's why in our green equation here, I make an explicit difference between the angular velocity of the coordinate system and angular velocity of a body. Okay? So, if we have chosen our coordinate system, now we need to compute all these things in this equation. Okay? So we need to specify what this is, and what this is in the coordinate system as shown here, and then do the cross product, and we'll have our solution. Right? So I am displaying this for the record. Choose coordinate system that precesses with the gyro but does not spin. Okay? And I am displaying this one for the record too. So this is, we already know. In that system, the inertia matrix will be constant. Due to symmetry, of course, this is the case. So off-diagonal components are equal to 0. And also, maybe we should remember that because of rotational symmetry, Ixx equals to Iyy. Okay? And now what's left is to evaluate this. So now the precession is steady, right? Steady means there is no accelerations and stuff, which means there is no change in angular momentum if axis of the coordinate system would not rotate, right? So this first bit is 0, obviously. So we are only interested in this bit. And we remember that this is the meaning of the capital omega, angular velocity of the coordinate system. So what are the components of that angular velocity in our system XYZ? Okay? This is the angular velocity of the coordinate system, capital omega. And what are the components of capital omega in XYZ coordinate system? Oh, come on. This you have to tell me. Well, Z component is omega cosine theta, right? X component is minus omega sine theta, right? And Y component is nothing. Okay, so this is now our angular velocity of the coordinate system, minus omega sine theta I, nothing in J, and omega cosine theta in K direction. Okay? Now, omega is the angular velocity of our gyro, lowercase omega. So what are the components of lowercase omega? What's the lowercase omega? The angular velocity of the gyro. Well, the idea 0, phi dot, not good, because this is not the total angular velocity of our gyro, because it also precesses, right? It's spin plus precession. So now, girls and boys, remember that angular velocity is a vector, the same as linear velocity, which means you just add angular velocity as vectors the same as you add linear velocities of vectors, which means that the angular velocity of our gyro is angular velocity due to spin plus angular velocity due to precession, just added as vectors. Okay? Which is something like this. Okay? So in x direction we have minus omega sine theta. In y direction we have nothing. And in z direction we have phi dot, which is due to spin, plus omega cosine theta, right? Piece of cake. So now we have our both omegas, and we can actually write immediately the equation for our angular momentum, okay? Which is, because the matrix is diagonal, it's just Ixx times the angular velocity in x, 0, and then Izz times the angular velocity in z direction. Piece of cake. Okay? So then, as we noted before, because precession is steady, this is 0, and we need to evaluate this. I think in primary school, people suggested that it's possible to compute vector products as determinant of matrix 3 by 3 set up this way. So I don't know. I use Mathematica for such things. But in the absence of Mathematica at the exam, maybe it's good to make sure, to be sure that you can take vector products at the exam. Okay, so now, if we look at this result, so we can, and then look at how H and how capital omega look, we can easily see that most of the stuff here is actually 0, right? Because if we look at I direction, here we have omega y, but omega y is 0, and here we have hy, but hy is 0. So this goes away. So there is nothing in x direction. If we look at z, we have hy here, but hy is 0, and omega y here, but omega y is 0. So this goes away. So the only thing that is left to worry about is the y component, okay? Or the thing along j. Okay? So if you actually do it, sometimes I ask people at the lecture to actually do the algebra, but luckily for you, not today, right? So if you actually substitute the values, so as we said, nothing in x direction, nothing in z direction, and this is what we get in y direction. Okay? Now, I'll repeat here that the meaning of the green equations as compared to the meaning of the Newton's second law is that this is the motion, the left-hand side is the motion and the mass distribution, and the right-hand side are real forces, which means that to maintain or produce steady precession of a gyroscope, as in this picture, you need a real moment acting along y direction. Okay? Somebody or something must be sitting there and acting with this moment on the gyro. This is the moment acting on the gyro. Okay? So the red stuff is this line for y direction rewritten slightly. So you take omega phi dot sine theta out of the bracket, and then you get this stuff inside the bracket. Okay, so again, very quickly, capital omega is the angular velocity of precession, normally low. Phi dot is the angular velocity of spin, normally high. Theta is that angle between axis of precession and axis of spin. And then IZZ and IXX are entries in the inertia matrix. Now, normally, IZZ is larger than IXX, and therefore, normally, tau y is positive. Okay? So, if we look at this picture, again, we get a positive torque acting about y, along y direction. Okay? So, if we use a right-hand side rule, well, my hand is too big for this, right? So we are acting along y. We are trying to increase angle theta, right? So the moment that acts like as if tried to increase angle theta fails to increase angle theta, unfortunately, but produces the precession around the axis, vertical axis. Okay? This is actually what we saw Well, what we actually didn't see, but we considered that spinning wheel on the string, right? The gravity was acting as if trying to increase that angle theta, but it wasn't dropping, it was precessing, right? So this is what we are seeing here now. Anyone who has trouble, as myself, with visualizing stuff does not need to visualize anything anymore, because we have algebra in support of it, and then it's the red equation, it is what it's saying, right? Even if you don't believe all these pictures, you will have to believe the equation, okay? So this is the equation which we will later use to solve our case study, okay? For the gyroscopic grinding mill. But now we will consider what's happening for the gyro, okay? So the first thing which happens for the gyro is that the angular velocity of spin will be in the thousands of RPMs, and the angular velocity of precession will be very small, which means this red bit is becoming very close to zero. Omega divided by phi dot is becoming zero, essentially, and therefore this thing goes away, and we are getting just this, okay? And then the second thing we note, for many practical cases, the angle theta is 90 degrees, as was in the case I showed, right? The angle between the axis of precession and the axis of spin is 90 degrees, right? So sine of theta is 1, okay? And this is the magical equation. Angular velocity of precession proportional to the torque acting along y direction. And this is a proportionality constant which we know, because we know the velocity of spin and we know the inertia around z, okay? Now, I'm surprised that nobody is fainting now, because I'm saying that the moment is not proportional to any acceleration, but to the velocity, and actually in a completely different direction, right? Moment along y proportional to angular velocity again around z1, or for theta equal to 90 degrees, say around z, okay? So, and it's true. First, you have seen it during the lab. Second, you have seen it when I hang the weights on it. And now you can see the equations. But totally, so true, but totally counterintuitive, okay? So, this is the real external torque acting on the gyro. Now, of course, you can rewrite this last equation like this. Okay, so omega, so angular velocity of precession equal to the gyroscopic torque divided by Izz times phi dot. This equation is the basis of an incredibly sensitive instrument for measuring angular velocities, which is called a rate gyro, okay? So you can imagine now, if you put that gyroscope in a fixed supports, any rotation of the axis will produce gyroscopic reaction in the supports. And gyroscopic reaction sometimes is called capital K, and it has the same value but opposite direction than the gyroscopic torque. And this gyroscopic reaction can be measured, for example, by strain gauges. So you can have strain gauges set up on the supports, you measure strain, and you have everything calibrated. So you get the forces, you get the torque. The torque is proportional to the angular velocity, so the velocity with which the axis of gyroscope is forced to move. Okay? So you have now the instrument, which is called the rate gyro, which measures the gyroscopic reaction, and then using this equation to give you the angular velocity. Okay? And these are extremely sensitive instruments. The unit of angular velocity used in these instruments is called the meru, or milli-earth rotation, okay? Which is, one meru is 360 degrees divided by 1 day, which, and then 10 to minus third, because it's milli, right? So it's 0.015 degrees per hour, angular velocity. Okay, and this is not the sensitivity, it's the unit that the instrument is using, right? So, normal rate gyros on commercial aircraft and things like this have accuracy of 10 to minus 2 meru, which means detects the angular velocity of something 0.00015 degree per hour. Okay? And space applications, sensitive military applications, 10 to minus 4. Okay? Which is angular velocity of one Earth rotation for 30,000 years. Okay? So you see that in a good rate gyro, this simplification of this equation does not affect much the actual theory, simplified theory, which is given here. Any questions about this? So you have a number of ideas, right? We have a first specialization of Euler's equations for a gyroscope. Second, we have a number of simplifications of a general red equation for high speed and then 90 degrees. Then we have an idea that we can use this to measure small angular velocities. Right? And we have this paradoxical situation when we have an external moment being proportional to angular velocity in some other direction, rather than to some kind of acceleration. Well, sometimes gyroscopes are set up in torque-free suspension, okay, so-called gimbals. Okay, so they are supported in such a way that there is no external moment that can be applied to the gyro. Okay, so if no external moment, the axis of the gyro will remain fixed whatever happens for eternity, right? So now you can use it for inertial guidance, right? So you have a gyro on the plane, put in gimbals, and then whatever the plane is doing, the direction of the gyro will remain constant. Okay, yeah?
What about gimbal lock?
What's gimbal lock? Gimbal, it's maybe I should, if I avoided using the term gimbal, I would just say torque-free suspension, the question wouldn't pop up. So, for example, imagine the idea of shooting the torpedo to the, yeah? Well, if you have your Euler's equations, okay, or maybe even even the general law, dH over dt equals to sum of torques, if there is no torques, there is no change. And if no change, the direction of the spin cannot change, ever. It's like these quasars for 100,000 years pointing one in the same direction. Okay, so the same on this. So imagine you are shooting a torpedo to the target, and you are in the First World War submarine. Okay, so you don't have that much computing power and electronics and sensing. So this is how they did it. They had a gyro on the torpedo. They would point the axis of the gyro to the target, okay, and spin the gyro, right? And then there would be a mechanical system, a mechanism that would connect that spinning gyro with the steering mechanism of the torpedo. So if the torpedo deviated from the set course by the axis of the gyro, it would activate some steering mechanism to put it back into the course. Okay? Fully and 100% mechanical system. Of course, not very adaptive. If the target moved, they would miss the target, but well, if the target didn't know they were shooting to it, then it was good enough. And of course, everybody likes spinning tops, right? So this is the spinning top we used as kids, right? So you spin it, okay, and then you leave it, and it doesn't want to drop, right? It begins some kind of dances on the floor. In any case, it doesn't want to drop. In the simplified perspective, you can say it's precessing, right? So if it doesn't move that much from the point of support, it will be precessing around the vertical axis. So this is how it looks like, okay? So this is the spinning top. This is the point on the floor, right? And now it is spinning rapidly around Z prime. And if it is off vertical, we have gravity acting, right? And therefore, and this will be equal in magnitude, or the reaction here will be equal to magnitude, in magnitude to gravity, because of course there's no acceleration of the center of mass. So these two forces will balance themselves as far as the magnitude is concerned, but because they are not collinear, they will produce the moment. And this moment, of course, is acting as if trying to increase angle theta. But as we have seen from the equations, it fails to increase angle theta. Instead, it creates the precession around the z-axis. Okay? So this is how the beautiful invention of spinning tops works. Okay? Any questions about this? This magic? Well, I can see there are questions, but they are being answered proficiently by other people in the audience, so nothing for me to do. Okay, so thank you, and see you on Monday. On Monday, we will solve our case study for the gyroscopic grinding mill.